students here spitting physics and rhymes, mega dumb jokes and answering questions. This song is proof that I take your suggestions. We can't do it live, so we hear online. Come on, y'all, it's morning time. So, good morning and good Wednesday, AP Physics. So I hope that you are able to start working your way through everything. We have about 2 weeks, I think 2 weeks from tomorrow until you take your exam. And I do want to go through some information from the exam with you guys today. I'm going to today kind of briefly go over the first part of the FRQ. I'm not going to cover all of the answers exactly. I want you to work your way through it. But if you're starting to get stuck, you're not understanding what they're asking you, or there's some parts that you don't understand, I'm going to try my best to kind of look through both of them with you and just kind of provide some details for you. So I'm going to go over some general stuff first, and then I'm going to go over, I'm going to read the questions and kind of give you some hints on some of it. And then at the end, I'm going to look at this email I've got that goes over kind of things that you guys need or that refers directly to the test. So I'm going to try to do all of this in about 10 to 15 minutes. I don't want to take forever because I know that you don't want to sit here and watch the video the whole time. And I'm sure you're looking out for your own sources and finding your own videos. Yeah, there's a lot of good sources out there. What you'll find is that a lot of this is just trying to basically understand the overall concepts and what the formula are trying to tell you. And so if you can kind of understand that more so than anything else, the work that goes along with it, a lot of that has to do with just understanding the overall idea of the concept. I don't know. It's not necessarily like you need to have a ton of math practice on how you do every type of problem. If you are pretty good with algebra in general, and you're good at, again, understanding kind of what the equations are asking you, it should be pretty straightforward. So let's take a look at some of the things that we are covering so far. So some of the things that we have covered so far, and I'm not going to go over the first thing, is what is omega, what is alpha, and what is theta. You should have covered that last week. I've gone over it in the last couple of videos and how do they relate, so just make sure you do see that. But those are part of a thing called rotational kinematics. Remember, kinematics is describing like just the mathematics of the motion, right? What are the actual key figures of the motions? So in this case, we're talking about what's the distance that I turn, that's theta, what's the speed at which I turn, and how does that change, right? And so that is omega and alpha, respectively. So just make sure you understand what those are, and make sure you can understand what torque is. Torque is basically saying rotational force. How much of this rotational force goes into turning my object? And we talked about an idea called linear or rotational momentum. So just make sure you've seen all of those things. If you have not up to this point, go back and look at some of my videos. I've covered it. Make sure you look at the videos I suggested for you, and we'll kind of go from there. But the main thing being that we know that if I want to turn something, I have to apply a torque to it. If I apply the only torque to it, it'll have this angular acceleration. And it'll have this angular acceleration because of this idea. It's basically Newton's second law. So we know that in Newton's first law, or Newton's second law for linear mechanics, we have this idea of my net force equals my mass times my acceleration, right? And then if I have any net force, in other words, an unbalanced force, I must have an acceleration, right? If I have any unbalanced force. But if two forces cancel out, I will have no acceleration. But it doesn't mean I'm not moving, right? I can be going at constant velocity. So we have that same idea, and this is Newton's second law for rotational motion, and it's pretty easy. It's the same basic idea, except we're just changing how we apply the idea to a certain extent. So we have this idea of my rotational, or my net torque, right? So net torque is rotational force, and so we're just taking this idea of saying, rather than pushing things left or right, how do I rotate something? So if I have something that's trying to rotate this way, but there's already something pushing to rotate it, then I have these two different torques, and I add them up to get this net torque. On the other side, we have the same basic idea. Rather than mass and acceleration, we have moment of inertia, and we have rotational acceleration, or angular acceleration. In this case, the main thing is to recognize that they're the same basic concept. One is, again, my acceleration, same basic idea, except for now it's talking about how does the speed at which I'm turning change. And this moment of inertia is another way of really saying rotational inertia, right? Another way of basically saying in linear motion, we have our mass, and that is my inertia, what's my resistance to change in motion. And then here, again, we have this moment of inertia, or rotational inertia, and the idea there is that the way my mass is arranged around this rotational center axis will dictate how much resistance I have to this change in motion, right? So for instance, let's just have two different things. So usually when we're talking about this idea, I equals mr squared, we're talking about this point mass going around the outside edge of a circle, right? And that's what the torque that it would be experiencing. So we're not really describing anything necessarily realistic, but let's say that I take this same point, and instead of it being a point mass, I have this huge rod, and this rod has this big circular mass on the end of it, right? And it's also rotating. Well, it's going to have a much larger moment of inertia. First of all, it's more massive, and more importantly, it's actually attached to the center. And so we have all this other mass to include into it. And then all of these pieces of mass are going to have their individual distances from this center. And so because of that, you're going to end up with this rotational inertia being larger because all of these pieces have this mass that resists sort of changes, right? So again, it would be harder to get this thing to keep moving than it would be to get this point object to keep moving, right? And that's the idea between talking about my angular momentum or my moment of inertia there. Cool. So let's go look at the problem. So I've got the problem pulled up here, and I want to take a look at a couple things with you and just make sure I have everything in order. Cool. Yeah, I think everything looks good so far. So let's go through the parts of the FRQ. So the FRQ is just basically talking about this idea with a couple other extra inserts, but it's this idea that if I want something to rotate, I have to have some sort of net torque on it, assuming it's at rest, because I need to give it this initial force so that it'll accelerate. Now, if I want something to be at equilibrium, rotational equilibrium, I need this net torque to be 0, right? And the way for me to get this net torque to be 0 is for me to have an offsetting torque, right? So in the problem, essentially what they're talking about is they have this sine, and this sine is on an axis point, right? So it's based on my elbow, and it wants to kind of fall like this. So they're going to try to hang it, right? That's kind of the idea. They want to hang it. And they want to hang it with a string to this top part here. Now, I want to say that I think that they kind of forget their own setup to the problem about halfway through. Because in like the first part of the FRQ, it's like, all right, we've got this, here we go. We've got this like wall, and then we've got the arm hanging from it and can kind of do this. And then, but it does have a wall. But then later on, they just go to talking about this arm, and they're like, okay, what if this arm swings? And they're like, well, the arm can swing back and forth. And you're like, in your earlier example, there was a wall there, so can it actually swing back and forth? And their answer basically requires you to say that it can swing back and forth to a certain extent. Not exactly, but I'll say that in the answer they give, they essentially go, well, it's going to go back and forth, so you know that, like, you're like, hey, it's not that. There's a wall there. It's going to go, wow, like that's it's going to happen. In any event. Yeah. So, again, getting back into the FRQ. In their physics classroom, students want to hang a heavy sign of mass ms, that's just massive sign, and length ls, length of sign, as shown in the figure above. The sign makes an angle with the wall. Without any support, the sign would rotate counterclockwise, while its pivot would remain connected to the wall. The students can connect one support cable vertically from one of the hooks above on the sign, indicated by the dotted lines in the diagram. They're not dotted lines, but that's fine. They're just solid lines. That doesn't matter. Anyway, so they've got these 3 hooks, right? And so they're saying which one of these 3 hooks would be the best place for us to put this, right? Where are we going to have the least amount of tension? Well, in this case, our tension is going to represent our force, the rotational force. And the idea is that torque is made up of a couple different pieces, right? And this should be all you really need to solve this particular part. I'll kind of let you do the rest of it. But what they're really saying is, remember, and this is on the formula sheet, so you just have to be able to identify this stuff. If you're literate in identifying your variables, you should just be able to go in there and find this. So torque is represented by my FR sine theta. So force is a component of one of the things that makes up my torque. And so what they're saying is, I want this number, this force number, to be the smallest, right? This torque has to be the same for all my scenarios, right? I have this sine. Sorry, I'll even draw it. And there's 1 point, 2 points, 3 points. For all 3 of these points, the torque has to be the same, right? I'm actually trying to put a counter torque up because gravity is pulling this thing down, right? Gravity wants this thing to rotate this direction. And so I'm trying to attach a string that says, like, it can't do that. I'm trying to apply this counter torque. So the torque I have to apply is going to be the same for all 3 positions, right? But I want this force to be as small as possible. Now, this sine, this angle over here, is going to be, for all three of these, is going to be 90 degrees. Let's go ahead and point that out, right? Because we want this thing to be flat, so when they're applying it, all three of them are going to be applied at 90 degrees. So that should be enough to get you through that portion of the question, and we'll move on to the next one and kind of go through it. But that should be enough to get you through that portion of the question, and again, we'll move on. Cool. So part B is where I have this thing where all of a sudden now it's on this pivot point and it's going to come back and go back and forth. And it says the students hang the sign with a cable, but the cable breaks and the sign rotates clockwise. In the example below, shows the sign at 3 different times as it's rotating. Indicate at which time, if any, the angular acceleration of the sign is at its greatest and whether or not it's the same at all times. So the main thing here is, and I'm even going to draw the same little picture they've got here. So let's just draw this picture here. Let's call this T3. Let's call this T2. Let's call this T1. Cool. I'm drawing a little thing for you guys over. So we know that based on Newton's second law of rotational motion, that our angular acceleration is going to be our net torque divided by our moment of inertia, right? This is just the same thing as saying F net over m is equal to A. It's literally kind of the same concept. So you should be pretty well versed in this idea. My net force divided by my mass gives me acceleration. So in this case, they're saying my net torque divided by my moment of inertia gives you my angular acceleration. Well, the rod's not going to change. It's not going to be any less massive, right? It's not going to gain any weight or lose any weight, and it's not going to get longer or shorter. So my acceleration is not going to be changed by my I, right? It's not going to go up or down by this I. And we can tell that again because I is not going to change. So if I want to know if this alpha is going to change, right? And they're asking, if they're saying it could not change, right? Is the acceleration going to be the same through all three of these things? And you're going to go, okay, I will not change, right? I equals mr squared. I equals mr squared, right? My mass will not change. The rod's going to stay the same mass. The radius will not change. So I won't change. So we know that that isn't going to change. What we're going to ask ourselves is, does the torque change? Okay? So since there is no cable, there's only one force applying a torque, which comes from where? Right? It comes from gravity. Right? At all these points, gravity is going to be pulling this thing. Gravity always acts down, right? Straight down. That's the key to solving the rest of this thing. Okay? So gravity always acts straight down, and it's the only thing applying a torque here, right? So in this case, we can go ahead and say that my net torque is equal to one force, 1 Fr sine theta. Right? My net torque is just one. There's only one of them. I don't have to add a bunch of them together. There's not going to be a positive one. There's not going to be a negative one. It's just going to be the force times the radius over the sine of theta. So again, I have one force that's applying this torque. I have one torque. Does it stay the same the whole time? That's what it's asking me, right? Right? Does my acceleration change at all? Does it change at all? Well, if it changes, it's going to change because the torque changes. Because I will not change. I is going to stay the same, okay? So what you're asking yourself is, does my torque change? In other words, does any component of this over here change? Because if it does, then my torque changes. And if my torque changes, then there will be a position in which I have a maximum amount of that, okay? All right. Cool. So we're going to get to part C. Part C, or B1, excuse me, B1, and then there's B2. Okay. So for B2, they're telling you they want you to come up with a way that says that alpha is equal to this thing. 3g sine theta over 2l. I'm going to show it to you, obviously. They want you to come up with that. They're literally telling you, can you come up with this? How do you come up with this, right? And then they tell you, hey, this rotational inertia is equal to this stuff, right? They say, hey, this rotational inertia, IS, because they're talking about of the sine, is equal to 1/3 mass of the sine, length of the sine squared. Now, we have a different formula here than I equals mr squared. That's because we have a different shape than a point mass around the outside, but they're giving it to us, right? So they're giving it to us, so we don't have to worry so much about that. So what they're saying is, can I come up with a formula given these pieces of information Given this piece of information, can I come up with a formula that looks like this? Well, let me go ahead and point out two things that you're going to need to know in order to be able to solve through this. The first thing is that my net torque is equal to I alpha. All right, so we have my net torque is equal to I alpha. Cool? So what we're going to do is we have our alpha. It's what we want. They gave us an equation for I. We're going to plug it in there. And then we're going to go say, hey, do I have an equation for what my net torque is? Well, we should have an equation for what my net torque is, right? I only have one torque on it. It's caused by gravity. So that's one piece of information, right? So we're going to plug in here. Here, we're going to plug in the I that they gave me. This is in the problem, right? Don't go looking for this somewhere else that's in the problem. And then for my torque, I'm going to go, oh, okay. So I'm going to add together all my torques. And remember, torque is FR sine theta. However many of them I have, I'm going to add all the ones that are in the same direction and subtract the ones that are in the opposite direction. And I'm going to go, okay, well, what are the forces that are causing this thing? I'm going to plug that force in. That's one piece of information you need to solve for this one. Okay. The other piece of information you might need to solve is, because if you do that, you're going to end up with one missing piece of information. But here's the thing that we want to remember. So let's put our wall on here and let's say, I don't know if you can see that or not, but we have this thing, right? Cool. This is the thing that's going to rotate around this direction. So you may be asking yourself, okay, I know I want to, gravity is applied to this thing, and I know that it's causing this torque, and you might be asking yourself, well, where does gravity get applied to, right? Because gravity, there's some piece of this here, there's a piece of this here, there's a piece of this here, there's a piece of this there. So how do I find out what my R is or my radius, right? Well, you might be tempted to say it's the entire length here. You might be tempted to say, well, that's the radius. Well, that's the radius for only the part that's all the way out on the edge, right? It's not the radius for the part that's all the way in the middle. So in order for us to answer that question, we just have to remember one thing from earlier in the year. Where does gravity act on an object? The center of mass. And in this case, because this thing weighs the same, this radius should be half of the length of our rod. Cool. Boom. Cool. Part C says we want to describe the angular velocity of the sign as it rotates, and it says, hey, here's an equation. They just give you an equation, and you can look at that because you need to. And it says, given that you need to look at that equation, right? Given that you have to go through and say, oh, okay, my angular velocity, should it just be this equation that I just got for my acceleration times time? Because, you know, velocity is acceleration times time. They're saying, does this actually make sense to our given problem? Does this actually model the velocity that we're going to see? So the thing we have to ask ourselves is, what should be happening with our velocity as it pertains to this object, right? So I start up here and I let go of it. Should I be at my maximum velocity here, or when I come down towards it, hit it? So the thing here that bothered me was that in their kind of answer, they're saying this thing will kind of do this. It'll swing back and forth. But again, remember my problem with it is it won't. There's a wall. That isn't like that affects the answer they gave in terms of their explanation, but it doesn't affect what the actual answer is. You can still use the idea I just gave you, which is, okay, so I'm going to take the equation they gave me and I'm going to plug some numbers into it and go, okay, what am I actually getting here? Like, what am I actually gaining out of plugging those numbers in? And here's what I mean by that. So take your numbers. They had this equation, and you have this g up here, and go, hey, all right, at 90 degrees, because this thing will be at 90 degrees, what's it going to be at? And then I'm going to drop it, and then it'll be at 0 degrees, the angle between the two of them. Here's what I mean by that. Okay, so when this thing is hanging out here, gravity's straight down, it'll be acting at it at 90 degrees. But as this thing starts to fall, it's not going to be acting at 90 degrees anymore, right? We're going to have these other angles. It'll be acting at this angle, right? And then we get here, straight down, the angle between gravity and the ground will be 0 degrees, right? That actually means that this is the angle that it's applied at. That's fine. 0 degrees when it's straight down. So plug those three numbers in and go, well, does that make sense for what I'm looking for? If I plug 0 degrees in down here, and I plug that information in, what is it going to give me? Does that make sense? And then you can ask yourself, is that what it should represent? And kind of go from there. As time increases, right, we're going this direction. So as time increases, what should my number look like? Right? Should I be speeding up or slowing down as I go to the 0 degrees? And does the equation they give me match that? Now, this took a lot longer than I wanted it to. That's fine. That's fine. And then you get to the last one, which is this graph. And with the graph, you want to make sure that you kind of evaluate the same pieces of information. Just really ask yourself, like, hey, given what the graph shows me, does any of that fit into what the equation is giving me, right? So you have to take a look at the graph, obviously. But what you want to ask yourself is, okay, so which one of these things is giving me a number that will reflect what I'm shown on the graph, right? So just go look at the equations. Essentially what I'm saying is some of these are giving you sine and cosine, and what you want to do is go, okay, so at the given angle it's showing me, would I expect that number, right? A roundabout way of saying that is, we have some sines and we have some cosines. And if we go and look at this thing, what we really want to ask ourselves is, okay, so cosine of 0 is 1, right? Cosine of 0 is 1. Sine of 0 is 0. So which one of those things is going to give me the answer that I'm looking for? I'm trying not to give everything away here. I want you to go look at it on your own. But essentially the idea is we have 4 different formula. I'm looking at them literally right now. And 2 of them have cosine and 2 of them have sine. So rule out which one you want for sine and which one you want for cosine, and then reevaluate which of the 2 of those fits the model better. And just look at the graph. Like, you don't really need to know how did they solve for it. You just need to look at those ideas. Because we have an angle, we have our maximum angle, and we have an angle of 0 degrees. Well, which one of those makes sense based on the sine or the cosine? Okay, so I'm going to try not to give away too much there. Make sure you are working your way through that the rest of this week. We're going to start doing a review on kinematics. If you guys want to, starting next week, please give me as much feedback as possible. If you want to go through new kinematics, if you want to spend more time on torque, we don't have a lot of time left, right? So we have this week, which we have to do on torque, right? Because we haven't really gone through it. And then we have next week, and then kind of like 3 days of the following week. In that 3 days of the following week, there's obviously no way that we're going to be able to cover like a bunch of stuff. I can post videos, but there's just no way that we're going to be able to cover a bunch of things. So having said that, if you would like me to cover something other than kinematics, if you would like me to cover literally anything else, you just have to let me know, and I can give you a good indication on I don't know, planning for that and how many videos I can record and that kind of stuff. I'm going to post this, try to get it up as soon as possible. I will try to I'm going to be hosting a meeting today. I'll try to get this up before the meeting. You know, cool. So I know I said I was going to do something else after I finish that. I don't remember what it is. I think I said I was going to talk about AP test stuff. I will just do that in another video, which I will record. Don't worry about that.